Hello and welcome to another episode in CSC 263 Database Management Systems at Adelphi University. This is the first of two videos about modeling. We're going to work our way up to how we model the data that will be present in an information system with the goal of understanding what that data would be so that in the next stage we can implement it and get our database ready to receive that kind of data. From the textbook, this covers material also found in Chapter 10. Before I go into the materials from the textbook, we have to talk a little bit about some of the ideas behind modeling. So let's start from the beginning. If we are going to build an information system that has a database backend, obviously we will need to know what kind of data we're going to be storing in that database. And that means that we need to put some thought into that. We have to make some choices as to how we are going to represent certain aspects of the real world into that database. And the process we use to get to that point is called conceptual modeling. Systems are incredibly complex things. Let's use that term for now. And that means that it is almost impossible for us to understand all the intricacies that are associated with the system. So first let's look at what a system is, then we'll look at what role a model plays in understanding a system, and then we'll look at a specific type of models called conceptual models. And like I said in the next video, we'll refine those conceptual models to data models. So first of all, what we have to acknowledge is that a system is a structured or a semi-structured collection of interacting people, artifacts, and processes. There are all kinds of different systems out there. Some of them are man-made systems, other ones are naturally occurring systems. Obviously, since we are talking about databases and database management systems, we are looking at systems that are artificially created. A system cannot exist in the void. A system is always used by, in the end, hopefully people or maybe other systems, and it's used in a particular way to accomplish a goal, and that we call a process. So when we look at a system as a whole, what we're looking for is how all of those people, those artifacts, and those processes interact, and what they need to get out of these systems. And when I say artifact, I basically mean anything that is man-made. A system is structured or semi-structured. It doesn't always mean that it's 100% clearly predictable, for example, how a system is going to work, although if we're dealing with man-made systems, there's usually more structure than less. So that's what a system is. It's just a bunch of things that work together. Now, there's a couple of principles that we have to adhere to. And that means that as we start designing systems, we always have to figure out where our system fits compared to the world around it. Every system is part of a larger system. For example, if I would be designing a new system to capture course registrations at Adelphi University, that new system would have to integrate with other existing systems. It would be part of the Adelphi University information technology landscape, which in its own right is connected, for example, to the internet. No matter what level we look at the system, there will always be a bigger system that we are going to be a part of. Very rarely do we see systems that are completely self-contained. And even then we are dealing with most likely users or some other inputs or outputs, and that again is the environment. So when we start figuring out how to design a system, we have to figure out what we pull into scope for our system, but also what we're going to leave external to our system. And making that decision, what goes into scope and what does not, is often one of the hardest decisions to make when you're designing a system. On the other hand, once I figured out what I want to do, I can also look at my system and I can decompose it into smaller systems. I can look in a lot more detail, for example, at a narrow aspect of that system. For example, I might only look at a particular user interface, or I might only look at a particular database, or maybe a specific system's function. And even though all the other components of the system that I'm designing still have to be designed and built. At that point, I choose to ignore them and almost see them as external to the little sub-function that I'm worrying about. And the benefit of that is that I can divide and conquer. I can solve each of these individual subsystems by themselves, and then at the end just put everything back together to create that overarching system. What happens, especially with systems that are around for a longer time, is that as they specialize, we add more features to it, and it's very specific features often. It also means that systems become a lot less flexible. And that's sometimes an issue, because a system that is not flexible cannot change with the environment and might become obsolete pretty quickly as a result of it. For example, right now we're in the middle of the COVID-19 pandemic. And that means that for many of the villages who operate town pools, they have to have a registration system in place that people can register for a particular time slot before they're allowed to come to that pool, even though they might be members. Most organizations, most villages probably did not have a system that was very specific to that, but they did have an event planning system where they might, for example, have people sign up for courses or for lectures or whatever it may be. And what we see quite a bit is that these systems are now being repurposed for basically saying, every day or every half day is going to be put into that system as a separate event for which people can register. Because that system is so flexible, we can do that. But had we built a system that could only be used for one very narrow specific purpose, we would have lost that flexibility. And when we design these systems, it is true that a system that is more specialized is usually more efficient at solving a problem, but it also means that we're almost inherently starting to build some obsoleteness into there, some legacy capabilities. So figuring out exactly where we want to be is a big part of design thinking. How flexible do I want to be versus how specialized do I want to be? Next is that systems grow. As we understand more or use the system more, we come up with these things like, oh, it would be really nice if the system could also do this or also do that. Very rarely will we go and say, you know what, I really haven't used this function in the system, let's just take it out. And as a result, systems get new features and new capabilities added to them, and systems grow, but they rarely shrink. Now, that in itself is a problem, because things that grow become more complex, and as they become more complex, they become harder to understand. But not only is that true, as systems grow, the system overhead also grows. And in many cases, the overhead of the system actually grows faster than the capabilities of the system. And so at some point, it might become a system that is such a monster application that it's almost impossible to make any changes to it just from the pure difficulty of doing so. And so the whole point of understanding systems and these tendencies of systems to grow, and as they grow maybe become more specialized and less flexible, are things we have to keep in mind when we design our systems, and we have to make decisions as to what we will go do with the system and how we're going to do it, and what we might choose not to do. Having some of these principles in mind as that's going on is always a very good exercise. Now, as systems grow and they become more complex, they also become much harder to understand. A typical example is, for example, the New York City subway system or the Long Island Railroad. Explain to me the system that is the Long Island Railroad. And you can take it from all different angles. You can take it from the angle of routes and timetables. You can take it from the route of railway carts and their numbers, the order in which they're connected to the train. You might take it in terms of sanitation and cleanliness. You may take it in terms of stations and station renovations, station repairs. We might take it in terms of personnel scheduling. All of these are different elements of the same system. And for us to have a comprehensive understanding of everything that's going on in a system, whether it's a system as complex as the Long Island Railroad, or maybe something a little smaller, as say the Adelphi University transportation system, it's still a very difficult system to understand. And so what we want to do is create models. And those models focus only on very narrow aspects of the system, the aspects that we care about or that are relevant for the problem that we are trying to solve. And we're going to try and capture that system by creating some form of a representation of that system. And we typically use some form of a symbolic representation to do that. The symbolic representation could take all kinds of forms. It could be just free text, natural language, but natural language is imprecise and ambiguous, so that's not often the best way of going about things, but it might be a good starting point. We might take mathematical formulas, which are a lot more precise, but less easy to understand if you're not a subject matter specialist. You might use computer programs, or you might use some symbolic notation in terms of diagrams. And that's what we see a lot happening, that we create diagrams that represent what those relevant aspects of the systems are. If we use diagrams, we typically identify a few primitives, things that have a predefined meaning in the model that we're going to be creating, and maybe there are some rules about how we can put those components together. Think, for example, electronics. We have a symbol for a resistor. We have a symbol for a capacitor. We have a symbol for a transistor. All of those things are components that we can put together according to specially defined rules. But by putting those components together into a new system, we can basically reason about that system before we've ever built it. A conceptual model, then, is a model that models out the concepts behind the system, and that means that we are not talking about technology or real-world implementation yet. We're only talking about technology agnostic decisions, agnostic representations of the physical world. And when we start creating those conceptual models in particular, we do that first of all to create understanding in our own heads. As we start playing with these symbols and putting them together, our understanding of all the ins and outs of this system enhances. But once we have created the model, we can also show the model to someone else and say, hey, listen, now that you know this modeling language too, can you take a look at that and see if I missed something or if I got it right? And so those are the two key aspects of why we want to do conceptual modeling. First is to enhance our understanding of what the system is like, even maybe before it's been built, so that's called an analysis component. And then second, to be able to communicate about the system, again, even maybe before it's been built. And once we've done that, now we have a pretty good understanding, and now we can start transitioning from technology agnostic to technology specific and get ready to actually build the system. Now, I mentioned that models are often diagrams, but keep in mind that a diagram is not always a model. Modeling is not about creating pretty pictures. It is about capturing what those pictures represent. It also means that we need to label those pictures very clearly. A picture without words is just a picture. And even though you might say a picture is worth more than 1,000 words, well, a picture with words is worth more than 1,000 words. If you take away all the words from a picture, you end up with an IKEA manual, and no one's good at those. So without that, it's hard to understand. So we want to make sure that we label all the elements of our diagram, but also that we give some accompanying text with our diagram that explains what it means and how it came to be. So in other words, when we create a model, what we're looking for is both the diagram with its labels as well as a separate narrative. A picture has to be pretty, a model does too, to an extent. So the model represents the system. And that means that if you have a lot of messiness in it and a lot of crisscrossing lines, unclear labels, your system in the end is going to suffer as a result of it. Keep your models simple, keep them clean, and maybe if it doesn't fit on a single page, split it up into two models. But avoid cluttering and stick to the same level of abstraction throughout your model. We'll deal with that, we'll practice with that in class as we start developing some data models and get some hands-on experience for these concepts that I'm giving you here.